In this video, I'm going to introduce modular arithmetic by defining it and giving some examples. We start by introducing the notion of Zn. This is the set of integers from 0 through n minus 1. For example, Z5 would be the set containing 0, 1, 2, 3, and 4. When we are referring to this set, you can see the way that Z is written here, the double line on the diagonal. This is significant. The notation Z with this double line is a symbol that means the integers. And then if we have the subscript n, it means the integers mod n. Now, we're going to delve into some of the details of this set and how to interact with it. It turns out that this is actually an extremely important concept in mathematics and computer science, but we have to start by learning more about it before we can look at some of the more impactful applications. So the word mod or modulo can informally be thought of as asking for the remainder when you divide one number by another. For example, when 5 is divided by 2, the remainder is 1, and we say 5 mod 2 is 1 or is equal to 1. Now let's formalize this definition. This is going to be a little dense, but the meaning is still essentially the same. We start with something called the division algorithm. This just means that when you have an integer a and any positive number n, then when you divide a by n, there's a quotient and a remainder. And you may write this as a equals qn plus r, q standing for quotient, r standing for remainder. And the remainder is always between 0 and n minus 1. The value of this remainder is the value of a mod n. We will use this expression a mod n to refer to this remainder throughout the rest of this video. I think that it makes more sense if we look through examples of this rather than looking at it symbolically. So let's go through several examples. To start, we're going to look at 100 mod 9. If we have 100 mod 9, we can use the division algorithm to check it, and we find that 100 is 11 times 9 plus 1, so 11 is the quotient, 1 is the remainder. And therefore, we say 100 mod 9 is 1. This second example is the same numbers, but in a different order. So we want to think about 9 mod 100. Since 100 does not go into 9 at all, the quotient is 0. So we're going to write this as 9 equals 0 times 100 plus 9. This just means that 9 is the remainder, 0 is a quotient, so 9 mod 100 is just 9. Of course, the same thing would happen if you chose any number larger than 9 to be the modulus. 9 mod 1000 is also 9, as well as 9 mod 1 billion. The examples are, of course, more interesting when the modulus is smaller than the number that we start with, and we're going to look at another example like that. Let's look at 63 mod 20. 63 is 3 times 20 plus 3, so the remainder is 3, and thus 63 mod 20 is 3. It can be tedious writing out the division every time, so a lot of times it's better to use shortcuts. And I'm going to introduce something that I'm going to refer to as the subtraction method. We'll do this by example. To find 63 mod 20, which we already know is 3, we can get the remainder by just subtracting 20 off of 63 until we get a number less than 20. So 63 minus 20 minus 20 minus 20 gives us 3, which is the same result as the previous example. As you do more examples of this, you'll see that the subtraction method can come in handy in a lot of contexts, including some I've listed here. I like to use it in what I call sneaky ways to make problems less complicated, and this is going to show up in the next examples. But let's start with a very straightforward example. 123 mod 100, that's just 23. You can find this by subtracting 100 off of 123, and you get the remainder of 23. Now let's add this into another example. What if I want to figure out 123 plus 194 mod 100? Don't add these numbers up if you want to make your life simpler. So don't go ahead and do 123 plus 194 and then subtract off 100 a bunch of times, because that's just a little bit harder. Not that much harder, but obviously as your numbers get bigger, these tricks become more and more useful. So instead of adding, I'm going to subtract from each part of the sum. 123 minus 100 is of course 23, and 194 minus 100 is 94. And now we're going to do something sneaky. Let's subtract 100 off another time. So 94 minus 100 is negative 6. Of course, you wouldn't normally want to do this, but it makes life easier in this particular case. So if we have 123 plus 194 mod 100, well, that's the same as 23 plus negative 6 mod 100. 23 plus negative 6 is just 17, so that's the answer. And we use subtraction to be a little bit sneaky by using the minus 6 instead of 94. There are a couple of rules worth noting that follow immediately from this example I just gave. So in general, if A mod n is equal to B, and C mod n is equal to D, then A plus C mod n is the same as B plus D. This is exactly what I just did. Instead of adding 123 and 194, I reduced both of them mod 100 by subtracting off 100, and then I added the results together. And you can always do this with modular arithmetic, so sometimes it makes sense to tackle the individual portions of a sum instead of doing the sum first. Similarly, this works with subtraction, so if A mod n is B and C mod n is D, then A minus C is the same as B minus D. So we can either add or subtract the results together and find the modulus, find the same remainder. Here's another sneaky application. What if we want to know 1 plus 2 plus 3 plus 4 plus 5 mod 6? Well, let's make this simpler by observing some things. 1 plus 5 is 6, which is 0 mod 6. 2 plus 4 is 6, which is 0 mod 6. So really in the sum of 5 numbers, 1 plus 5 is 0, 2 plus 4 is 0, and the only thing that remains is a 3. So 1 plus 2 plus 3 plus 4 plus 5 mod 6 is just 3. We won't show this here, but this actually is true in general for an even modulus. 2 more examples. If we were to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 mod 8, then the result would be 4. So 8 divided by 2. And also if we were to add up all of the numbers 1 through 99 mod 100, the result would be 50, so half of 100. I'm going to wrap this up by stating a couple more rules. The rules that we had earlier about addition and subtraction, we can do a similar thing with multiplication. So if A mod n is B and C mod n is D, then A times C mod n is the same as B times D mod n. Further, and this is really just an extrapolation of that last rule, if A and B are equal mod n, then A to the k is equal to B to the k mod n for any integer exponent k. And there is a lot more to that one can do with modular arithmetic, but hopefully this gives you a great starting point, and I'd encourage you to learn more from here.